It is my pleasure to introduce our tutorial speaker, Dr. Markus Christoph. He was born in Germany and received a degree in electrical engineering, diploma engineer from the Department of Telecommunications, University of Applied Sciences in Regensburg, Germany in 1998. Since 1998, he has been employed by Harman Becker Automotive Systems in Straubing, Germany, working as a researcher in diverse fields of digital signal processing and acoustics. In 2013, Markus has received a PhD degree from the Institute of Electrical and Information Engineering of the Technical Faculty, the Christian Albrechts University in Kiel, Germany, where he started his external industrial doctoral thesis in 2010. Dr. Christoph's main research interests are in the areas of audio and room acoustic equalization, digital signal processing, synthesis of sound, active noise control, coding and decoding of audio, dynamic equalization, speech enhancement, adaptive filtering, Acoustics, and so on. He has contributed to 2 books, several papers, and currently holds approximately, how many do you think? 100 patents. So let us welcome Dr. Markus Christoph and his tutorial.
Thank you, Michael, for the nice introduction, and hello and welcome to my tutorial. Maybe if I start, let me allow to find some words about my background. I mean, I'm coming from the acoustical side, and therefore, and from this point also, I'm more related in automotive. So I'm here, I would say, an exot by all these video gods that are around. So as I said, I'm really from the acoustical side, and they're from automotive. So here I try to also contribute to the consumer electronics, and therefore I made up my mind and said, okay, how do I see the future for in the side of audio for consumer electronics? And therefore I focused on home audio for this tutorial. First of all, I would like to give you the outline of my tutorial. First, to give you the introduction. Then let's talk about the current status. And then I would like to take you to the journey throughout the whole processing chain of audio, beginning with the source material, talking a little bit about formats, the quality aspects, also about the sense and the idea behind upmixers, several trends that can be seen in our area, and preliminary conclusions. Before we find out, going through these preliminary conclusions, where really, from my point of view, the problem is, and which can contribute to make things better in the future, then I would like to go into this main topic and want to dive a little bit deeper into it. And the main topic is then with room equalization. And there I also want to give you a current status. Then I would like to talk about the manual tuning. This is one of the possibilities how to tackle this problem. I want to talk about acoustic holography, multiple input, multiple output methods, and as well as wavefield synthesis, and finally higher order ambisonics, before I go into the outlook, where I present one of the possibilities how to solve nowadays also this problem. Okay, but now let's have a look at a normal situation in home audio systems. So this is just a snapshot of a typical room, a living room, where you have a table, where you have a television, and you have randomly set speakers. I mean, this is, I would say, a typical case, because you never place the speakers like given or recommended in any standard. Due to the fact that you do not have the room, you do not have the possibilities to place it where they actually should belong regarding the standards. Therefore, you just place them where you have some spots, and that's the fact. And But what you have is also, we call it in the acoustical society, the sweet spot, or here a sweet area, meaning you can sit here on this place, or you can lay at the sofa, having your head and your ears always in a certain area that can be predicted in advance. And also the rooms that we have to deal with are always different. Some have maybe a carpet, others have a stone floor, some others might have a wooden floor, others have a high ceiling, so it means a high volume in the room. Others have, I don't know, they're surrounded by windows that are heavily scattering the acoustical sound. So you never know what's really in the room, whereas the system should behave like in the standard. So the problem is now, do we have possibilities to improve the acoustical quality in, let's say, in any unknown room? And predict, for example, a standardized 5.1 setup. And I would like to answer this question in this tutorial, and want to give an answer also how this can be achieved. So, but first of all, let's give you an overview over the audio chain that we are talking about. And then let's also talk about how and where can we really put some improvement for the acoustical quality. First of all, I would like to start with the signal source, but actually this is not the beginning. The beginning starts even before that. This means in the recording domain. So the recording, if the recording engineer is delivering not a very good quality, then everything else is senseless, because you cannot make out of a bad source material anything sounding good. So here I just say that I hope that the recording engineer was doing a good job, and the source material here only have a CD as an example is used. Then this one is given to any playback device. It can be USB, it can be a phone, it can be a CD player, whatever. Doesn't matter. Then it is sent to the amplifier, to the speaker, through the room to the ear. So now, if we go step by step through this acoustical chain and then analyze it, we will find out very quickly where we really have a drawback and where we can improve things. So let's start with the source material. We have a manifold of source materials nowadays available, especially all the compressed formats that are there. Here I just have a snapshot, always taking into account what is actually used by people. I mean, it's typical, if you're at home, at least in my home, I still use very often CD. It's very easy to handle. You have a whole pile of it. You just put it into the CD player, that's it. So if I take CD as a normal standard format, it is recorded usually with 44.1 kilohertz and has a dynamic of 16 bits. What's also very popular, and I have to apologize, but I'm also a very heavy user of MP3. We should also take a look at the compressed formats, and they are scalable. So therefore, they can vary between 8 and 48 kilohertz, and have a bit rate of 8 to 320 kilobits per second. So therefore, it is not so easy to say, compressed formats are bad, because it depends whether they are recorded with high sampling rates and high bit rates. So if you have a high bit rate, for example, 320 kilohertz or 256 and 48 kilohertz, I guess nobody, or it's really rare that somebody can distinguish a quality difference between a real CD and such a high quality MP3 formatted signal. What also is used very heavily, it's FM stereo, at least in Europe, because their AM is more or less dead. But FM is the standard. If you go into the car and you have not a particular source where you want to listen to, you just go in, put on the radio and you listen to music. But what about the background of FM? So FM has a spectral bandwidth of 15 kilohertz and a dynamic depending on sound quality, so it's scalable, but has a maximum of approximately 70 dB. And here in the US, satellite radio is a big thing. Europe, unfortunately not, but here it should be able to be transformed by CD quality, but there are some problems, especially if you're in an urban surrounding, you have high buildings and you lose signals, and okay, then the quality can be as good as it is. If you lose the signal, you don't want to have it. So therefore, but this is a really common selection of signals that we have to deal with. So generally, the source material should always cover, and this also accounts for the whole audio chain, should also cover the limitations of our hearing system. So we also have to know the limits of our hearing system. So I do not go into detail of all the different aspects of our hearing system, but the main prominent ones are definitely the spectral range. This means the bandwidth as well as the dynamic. So, and our hearing system is usually said to have a bandwidth of 20 to 20. This means 20 hertz to 20 kilohertz, which is actually not true, because who is able to really hear 20 kilohertz? Maybe it's a small infant. But as soon as you are a teenager, maybe you can hear 16 kilohertz. I guess this is more realistic to say. But the dynamic range is really very high. So it's 130 dBs. This is has the highest dynamic of all of our senses. So the hearing system is really has really a huge dynamic. And this dynamic has to be also covered with the formats. And here we have a lack, because basically none of all the formats can cover the dynamic of our hearing system, whereas the spectral range, this means the bandwidth, is handled with a normal CD without any problems. So therefore I would say, spectral-wise, we are fine with the source material, but dynamic-wise, there is something we could improve. So this is probably also one of the reasons why nowadays HD audio is a big thing. And I don't know if you have been to the CES, and I guess Sony is really promoting heavily HD audio, and this has also some sense. And one of the senses is the bandwidth has to be covered, because you have some problem for FM stereo, but you also have some problems with MP3 depending on the sampling rates they're using. But more or less it is because of the dynamic. Because the dynamic, here we have a lack. And HD audio is closing this gap. Therefore, it makes sense to have HD audio, just at least to be sure that the whole ranges of our hearing systems are covered. So now let's talk about the typical formats that can be found nowadays found. And actually, there are only two. There are a whole bunch of formats available and standardized, but what we actually use by far more than 99% is stereo format. If you listen to FM audio, if you listen to MP3, if you listen to whatever, over and far more than 99% is coded in stereo. And the ITU standard says you ought to have to follow this setup of the speaker to cover exactly what is recorded on your source material. So this means if you have speakers left and right in an angle of plus minus 30 degrees, then you're following the standard. If the speakers have a distance that equals exactly the radius, this means the distance to the place where your head is. And the other format, which comes mostly along with videos, is 5.1. I mean, many or most of you might have a Blu-ray player, whatever, able to play 5.1 materials, and also in almost all DVDs or Blu-rays, 5.1 is encoded. So you have the material, the acoustical material, to play it. So, and the other standard, the 5.1 standard, is following this ITU standard. So you have again the plus minus 30 degree. Now you have also in the middle of it, you have a center, And at an angle of plus minus 110 degrees, you have the surround speakers. So you have left front, right front, center, left surround, and right surround. And the dot 1, this is the subwoofer. It is not specified where you place it because it doesn't really matter as long as it plays approximately below 100 hertz. So you have now one more or less standard for normal audio, and you have also now a quasi standard for video. But that's about it. All the rest, I mean, as I said, there are lots of standards at the market, but those are the most prominent ones. And I'm talking about really the things that are real, that are at home, and not something that could be. Okay, if we take the human auditory system as a guidance, the following statements we can make. So the source material usually is no problem as long as it has at least 16-bit or better 24 bits. This means as soon as we switch to HD audio, having at least 24 bits, we are fine, because then both limitations of our hearing system are covered. This means the bandwidth of 20 to 20 as well as the 130 dB are easily covered by those numbers. I mean, you know, 1 bit is about 6 dB, so therefore with 24 bit we have 144 dB of dynamic available. Therefore, we have a little bit headroom to cover the complete dynamic range of our hearing system. The playback device, we only have to look more or less nowadays at two different areas. And the one is the AD-D8 converter, and the other one is the performance of the power ICs. Both of them nowadays can easily cope with those limitations. Therefore, also from this point of view, we have not a big an issue. Therefore, there is, at least from my point of view, no need to really put hand in this area. This means playback device or amplifier, they are fine. Speakers, that's a little bit different story. They have no problem covering the spectral range from 20 to 20, but the dynamic range, especially at low frequency, can be a problem, because especially there we need a high sound pressure to trigger our hearing system, because as you probably know, our hearing system is it's like you know probably the threshold of hearing and the form of it, and therefore it says that at low spectral areas our hearing system needs a high power or sound pressure level to be triggered. Therefore, you have to have big boxes to generate this sound pressure level in order to trigger your hearing system, and therefore to cover all the dynamic range. Therefore, boxes or speakers, this is an area where we can improve. But nowadays, I would say if you have a good speaker, we are almost fine, but here there is something we should and could do. But then there's the room and the big unknown. So we would not have a problem if our rooms were all standardized. So if we have a room as described in one of the ITU standards, no problem. We would not have, let's say, the necessity to do room equalization, but this is just a dream. Nobody of us probably has an ITU standardized room at home. Therefore, we have to do something like this against this. You can also replicate the ITU defined standards to place your speakers. This helps a lot, but it doesn't solve the problem, because there's still some unknown reverberation going on where you want to improve. And you have also then, after the room, the cabling and connectors. I know many others say, say this is a very magic area. I'm a scientist and I said this is bullshit, because we have enough. You know, copper is good enough. If you have gold-coated connectors, no problem. You don't need anything else. That's really no big deal. So cabling, connectors, no matter what others say, they do not make a difference. So if you now draw a conclusion, the only remaining parts that can be or should be improved is the speaker and the room and the interaction of both. Okay, then we have also the purpose of an upmixer. So what is an upmixer? An upmixer is a signal processing block that makes out of a stereo signal, for example, a 5.1 or any other format. This is good if you have, for example, invested into a 5.1 audio system, but you only play stereo music and said, okay, I want to have surround, even or nevertheless, if I only have stereo as input signal, and an upmixer is exactly doing this. So it takes the stereo and it upmixes to any format, for example, the 5.1, and then you can use your acoustical setup as it is and enjoy surrounding effects, even if it is not coded in the beginning. And there are many, and the purposes for the upmixer it is that you get this surround effect. This means it increases the envelopment. And there's a horizontal localization. Now, this means if you have a virtual stage in front of you, you want to have, let's say, an organized stage. You want to have it like in a real concert. Here there's a singer, here there's a guitar player, here there's a drummer. And you want to separate it on your virtual stage. And if you can localize this, at least in a horizontal area, then this is a sign for good localization. And it stabilizes the sound stage. So this means if you have a singer and not a very good set up acoustical system, then it might happen that the singer changes its location depending on the spectral content he is just using. And this is then called an unstable stage, acoustical stage. And if this is frequency independent, it is stabilized, and thus such upmixers can also help in this regard. So, but how does it work? So we have an active or passive upmixing matrix depending on the speaker setup. So this means this upmixer really has to know what kind of speakers do you have, how many speakers do you have. And sometimes such upmixers also ask for where are they located at. I will not talk about those upmixers. They can be found, for example, in the direct, so-called direct systems. This means directional audio coding system. But anyhow, you should just know here that something like this exists. The active upmixers that are out there, they are constantly analyzing the input signal and then generating something we call a steering vector to just estimate where should the sound come from this virtual stage. And depending on this information, they send the signal to certain speakers in the room where they have the information where they are located at. The passive upmixers, they do not suffer under this problem, because if you constantly analyze a signal, and if the signal is not coded in a right way or has some coding errors, it is prone to have some steering, or to create steering errors. This means you have then jumps of acoustical scene. So just to give you an example, the guitar player can move all of a sudden from this to this position and then back. And this is disturbing, such artifacts. And the bad story behind it is the more environmental or the more enveloping effect you have, this means the more wow effects this upmixer creates, the more prone it is for such steering artifacts. But as I said, passive upmixers do not suffer under this problem, but they are suffering under a different problem. Because they do not distinguish between the input signals. So therefore, they handle all the same. So if you have, for example, just a mono female voice that has a very clear picture without any reverberation, whatever, it is exactly handled the same way as if you have a source material that is very surrounding. So it can happen that, for example, such a clearly localizable single voice is spread throughout the room, and then it makes also an unnatural behavior because it sounds surrounding, whereas it should not. So what should we do? I mean, both has its advantages and both have its disadvantages, but at least it helps to cope with the system you have and the source material you have also at your disposal. So which upmixers are there? There are tons of it, but the most known ones are, for example, DTS, THX, the Dolby Prologic. There are different versions. It's also called, or Dolby Digital, it's also called AC3, Dolby Surround, and from my company, it's also probably known Logic 7, Quantum Logic 3D, and so on. But there are many out there. To give you just an example how it works, I took one short-time Fourier transformed-based upmixing decoder. This has nothing to do with Dolby or whatever. It's just to give you an example how it works. So you have the left and right input signal. You transform it into the spectral domain. Then you make the correlation. And then out of those information, you make the ambient extraction. The ambient extraction, this means what is not called a direct sound. That should really be maneuvered to one of a singer, of a guitar player or whatever, but is contributing to the envelopment of the whole sound. This is then delivered to the surround speakers. All the uncorrelated parts of the left and right input signal, they are considered to contribute to the ambience. And therefore, they are distinctly, they are only delivered to the surround speakers. For the front ones that are left, and this means front left, front right, and center, you have now a steering vector that you calculate out of the left and right correlated parts. Then you make a center extraction, and then you send those three parts, depending on the steering vector that you calculate over frequencies, to those speakers. And all this happens dependent on spectral parts as well as timing parts. So this is a time spectral processing that happens to really place shares of the input signals to the speakers that are available. But even this upmixer now expects that the output signals or the output speakers are located regarding the ITU standard. So the input signal are regarded to have ITU standard, as I showed before, plus minus 30 degrees, whereas the output speakers, it is expected that they are also arranged regarding the standard. So if you are not having this standard, which is typical the case, then this upmixer is also not working perfectly well. So this problem of room equalization still remains. So the conclusion is that the upmixer makes a first attempt to deal with the room and the speakers available in it. But in secret, it was, as I said, it was assumed that the source material will be played back with the system in compliance with the underlying standard, which is not the case. Though if we would have a system in compliance with the underlying standard, no further processing again would be used or would be necessary. Okay, so now let's talk about some trends. And the trends, it's very easy to say, goes to more speaker, more enveloping, and one of the most prominent nowadays and commercialized is Auro 3D. They are showing up in different formats, as well as this 22.2 format. Here, as you can say we are dealing with layers. Here you can find the 5.1 ITU standardized setup, the 5.1, and 1 meter above or so, again, the same one. So now you add some height speakers, and in the top line of the Aura 3D, we have another speaker which is right in top of you, which is also called the voice of God. Whereas in the 2220 you have also layers, but now the layers are arranged in this way. This means you have here some at the bottom the subwoofers. That it's only 3 layers because woofers usually it's enough if they are in stereo. Then you have the horizontal layer, which is comparable, let's say, to the 5.1, but now you put yet another one in between the center and the front left and the front right. Here you have the side ones, which are usually good for increasing the lateral sound imaging, as well as the rear speakers with a rear center. And then you have also now a top layer to increase the localization even in the vertical domain, again with a top center speaker, which is equivalent to the voice of God for the Aura 3D. But there is more to come, and the new upcoming standard in this part is the MPEG H Part 3. And let's say the point behind this is that this standard now tries to cover many different speaker setups with the input material. So therefore, it should be very flexible. So you could have any source material in any speaker layout, and it should be able to handle it. And it should be able to automatically adapt to the audio program material, to the target number of loudspeakers in a given listener and venue. This is exactly what we are talking about right now. I mean, this standard is almost, it's on its way, so it's not finalized yet, but it doesn't give the solutions. It just said, we would like to have it like this. And audio rendering, I haven't mentioned it yet, is also covered in this standard. This means a rendering in my area, so it means in the audio area, is you have a virtual source and you can just put it anywhere in the room, virtually in 3D. If you have enough speakers, like in the 22.2 setup, you can place it above, beside, behind, wherever. And this can be done also dynamically. This means it's thinkable that the customer, I don't know, has an app on its smartphone and can just place virtual speakers anywhere in the room, if this works. Yes?
Does it matter for the HD or standard resolution for the compression standard? Is it like the target for HD audio or for the...
No, it doesn't really matter if this is HD audio. So it has to do with the sound field management. So it doesn't really say something about the formats that has to be used. Okay. And now let's go to the preliminary conclusion. So we have the source material. The source material usually, as I said, by far more than 99% is in stereo. Then we have an upmixer that can, let's say, convert this source material into any format that is available at home. And then we have the unknown, that we have to fill in this unknown block. And then we have the connection to the room. That's about it. But what's really important, there's also a direct way from the source material to this one, and this is actually headphone. This is one of the reasons why headphones are so important nowadays and gain more and more influence. Because if we have the direct way, if we have good headphones taking the biometrical individual capabilities of the users into account, they can sound excellent. And then we don't need anything else. If somebody is good and fine with headphones, we can really make a very shortcut here and can say, you have an excellent sound quality. We can also make rendering or even soundstage manipulations if you go the direct way. But this is a different topic. And in this tutorial, I concentrate really on the room. So therefore, but I just wanted to mention and want to give you a hint why headphones are such a big deal nowadays. So, and the reason for this block, or what is the meaning behind this block? It is to transform. Now, this block should be able to convert any possible real speaker setup as close as possible to the desired underlying standard. Though the Upmixer, for example, makes from 2.0 to 5.1, and this block should make from the room as close as possible to the standard. That's it. This is the topic of this block. And this is what we call room equalization. So this block, what we really want to talk about is room equalization. The purpose of it is to eliminate the detrimental influence of the room, or to transform the current room into a standardized room. And there exist many ways to tackle this problem, and some of them are already available. And what we would like to have is an automated calibration, following the best practice. Now, one of the methods that are available are the automated calibration methods following a best practice principle. I will talk about this in a minute. Other companies also provide the possibility of tuning the system manually. I mean, this is actually the job of an acoustician. And as long as, let's say, the end consumer has really a deep knowledge in what he is doing, you can really gain good sounding systems out of it. But it really asks for experience and a good listening capability. Yes, and for that reason, some companies do really offer also a service where they send an acoustician to an end customer at home, and he is adjusting it just by using his expertise. But there are also mathematically close possibilities to tackle this problem, which eventually deliver even better results than the most experienced acoustician is able to do. And one of the possibilities that are available nowadays, they are looking like this. So you have in your, let's say, 5.1 system also a microphone in the package. You place it where you would like to sit or to be. Here, for example, it's this spot at your sofa. This is the sweet spot. Then there is a measurement signal created and played over the whole system, and you get the measurements or the transfer paths from each speaker to this microphone, to this, and then you just place microphones at a certain distance along the curtain. You have some room in between, and you just play back all the things that the microphones record here by some speakers arranged in the same line. And what happens is that in the other room behind, you got the impression that you have a virtual source right as if you would be in the real room having the source here at this point of the stage. So that's actually the idea behind acoustic holography. So the basic principle, as I said, is you go along a line, record it, and then you play it back. And just assuming that these are all perfectly linear systems, of course. And this was, again, thought by Burkhardt, 1988. And now, if you have this information available, you can separate those lines and put a matrix of filter in between. And this processor is then, let's say, the idea behind the new version of the wave field synthesis. So you can, the acoustic holography is also known as auralization. And the target is to replicate wave fields in a real room. But in this replication can be based on a recording in yet another room, the source room, or most of the time in terms of wavefield synthesis, it is based on simulation. So you just have a virtual room on your computer, simulated, you place there acoustical source, and then you play this back in a real room using those wavefield synthesis filters, with the effect that you have now in the real room the wavefield as simulated in your virtual source room. It can be used, so now let's talk about some examples. So what is it good for? It can be, for example, used for acoustical documentation, meaning if you have, for example, I mean, I'm from the automotive area, if you have a car that is really sounding good, you want to document it. This means you want to just record it, and you want to take this acoustics into your studio room, and you want to have exactly the same acoustical feeling as you had in the car. And this is possible with such audiorization techniques. You can use it also for virtual tuning. In the automotive industry, prototyped cars are usually used to make the tuning, and the tuning are usually made by acousticians. But prototype cars are expensive. Therefore, they are only available for a limited of time. If you have the possibility of making acoustical documentation, so if you can virtually create a room acoustically, then you have much more time to make your adjustments and get a much better impression out of it or in a result. So therefore, you gain time, and you don't need to use so many prototypes, which can save costs. And of course, it can also be used for room compensation, what we are interested in mainly here now for this tutorial. And by the end of the day, also for an automated tuning. So we can also get rid of the acoustician by the end of the day. There are two forms how to realize it. It is one is data-based. This is able to create a one-by-one replica. But it is also possible to make it in a model-based way. So which then allows also for acoustical rendering. So you know this virtual sources that can be moved around freely in the room and so on. Though there are many possibilities to realize it, but one of them is the MIMO systems, the multiple input, multiple output system, the wavefield synthesis, as well as the higher orbit ambisonics. Whereas the MIMO system belongs to the data-based one. This means you can use a MIMO system and can have a one-by-one replica. The good thing about it is that it is completely free of the speaker setup. Whereas the wavefield synthesis or higher ambisonics versions, they ask for a certain speaker layout, but then they can create a model-based version which has more flexibility. So the target room can be a real room, but it can also be, for example, headphone. So as I already mentioned, most of those possibilities, say, require specific speaker setups. It's wavefield synthesis and higher audio ambisonics. But others, and the problem is that in practical realization, speaker setups are arbitrary. So therefore, a MIMO system is probably nowadays the only one who can directly handle this. But for the future, and we also talk about the future, those two should not be forgotten.
For the target room setup, and it makes sense for the real room, you have a size and you have microphones at different places. But for the headphone, the target room, how do you define the working size? In order to have, I mean, the sweet spot definitely is at your ears. Regarding the surround sound 3D, how would you describe the target room setup?
It is like this. I mean, if you have, let's say, a model, and you can place a sphere in the size of a head, so this means about an 80 centimeter diameter solid sphere in it, where you have about 80 centimeters distance between two microphone positions. It's easy to simulate the wave fields occurrences at those places. And then if you virtually move the speakers away, you have exactly the influence at this place. And then if you have well-compensated headphones, where you take the individual concha and especially ear canal deficiencies into account by compensation, then you have exactly, after following this method, the room size that you desire.
So basically you are having this rhythm out of your head.
Yes. So,
Thank you.
okay. What is a MIMO system doing? So now we're following the same approach, going from the signal source to the upmixer. Now this unknown block is filled with the MIMO system, because a MIMO system can really delivering the room compensation we are searching for. This means it can create a virtual ITU standard following speaker setup, such that you have at the sweet spot the feelings that you are surrounded by a speaker, by speakers following the ITU standard. Yeah. And if you are able to create that, then the upmixer is doing exactly its job. This means it's bringing its stereo system to a 5.1 ITU standardized following system, which we can create using the MIMO system and any arbitrary speaker setup. Of course, this does not work perfectly, but it can make it, it can create it as close to the standard as possible. I mean, we cannot beat physics. I mean, this means if I only have 5 speakers in front of me, I will never have a sound coming behind me. So therefore, I have to follow some at least rudimentary physical limitations. This means I have to somehow be surrounded by speakers, but they do not have to follow the standard, and also do not have to have an exact distance to the sweet spot. If this happens, then the MIMO system can create really stunning acoustical performance. Okay. As I said, the MIMO system belongs to the data-driven version. This is a data-based representation, so therefore, unfortunately, no acoustical rendering is possible. So what also has to be done is that we have to make multiple measurements at the sweet spot. And also, if we do it right, we have to take the human body as well as human head into account by doing it. Okay, but how does it work? Now let's go a little bit into the math. So here you can actually see a multiple error FXLMS algorithm. This means a multiple error filtered input least mean square. This means I have a source signal which goes through a primary room. This means this is my listening room. This is my source room. This can, for example, be a good listening room. This can also be a simulated room. Or it can also, in the ideal case, be a ITU standardized room, where I make the recordings, and I said, I would like any room, by using this filter, sound like this target room. This source room. And therefore, I place a number of microphones at the sweet spot, and the number is here M microphones, and I just get the difference between the desired signals and the recorded signals, and the error signals that result out of it, they feed this multiple error least mean square adaptive system, creating K equalization filters, and then the result will be this W from C matrix, which means this matrix is doing then the room compensation for me, delivering what is desired. This means this virtual 5.1 setup at the sweet spot. So, but how, I mean, after this adaptation has ended, we have, let's say, the best approximation of a filter set that is able to create, in this case, 5.1 virtual sources in any room at a sweet spot. But how is it applied? So it is applied by doing it several times. This means out of the Upmixer, we get 5.1 output signals. Each output signal is actually there to create one virtual source. For example, the left front one should create a virtual speaker at this position. And for that, I need a filter using all available speakers. Of course, those speakers behind will not be driven at all. Can happen. But maybe they have to be used at least slightly. You never know. Therefore, I need 5.1 filter sets or filter matrices, each one for each input. And now if I have a 5.1, so I need 6 sets of MIMO filters or room equalization filters. For each virtual source, it's one set of filters. It's so easy. So let's go to the properties of the MIMO system. So it is very flexible. It does indeed not need a special speaker setup. So we can neither for the recording nor for the playback room. So I can also use anything. So it doesn't have to follow any standard. The only reason why I want to follow a standard is because of the recording and not because of the setup of the Upmixer, but not by its own. Usually it's so flexible it can handle anything. Yeah, and I already mentioned that the reference transfer functions, which was stored in the matrix P from Z, stores or can originate from a real measurement, but it can also originate from a simulation. The only requirement that has to be fulfilled or met is that exactly the same recording device is used in the target as well as in the source room. As long as we follow this, we can use exactly the adaptation process that I showed a minute before. The recordings can be made with any microphone array, so it can be a planar array, it can be line array, or a circular array, whatever, just name it, or a spherical one. But as I said, they only have to be the same for the measurements in the source as well as in the target room. So even one microphone, measurements with one microphone are possible if you use exactly the same way how to measure it. So if you have, let's say, one rod and a step motor that is driving exactly at the same positions in the source as in the target room, you can do exactly the same stuff with just one microphone. Doesn't really matter. Yeah, and as what I also said is that almost optimal results can be achieved by following this approach, but still it has some limitations by just delivering a one-by-one image. I mean, this is usually good enough, especially if we talk about home acoustic systems, because there usually it does not change very often, I would say. You just place the speakers once, and once you have set it up, you make the measurements, you're just following the standard, and then you press the button, it is calculated, and that's it. So therefore, this is not a big limitation for our approach, but I want to also look into the future, and therefore I'm really interested in the rendering. And to do the rendering, we have to follow another standard, or another possibility, and this is, for example, wavefield synthesis. And the basic principle, it stems from Huygens from 1678, and here it is shown what it does. Though you have one source, the source is radiating a sound wave, and along one line you want to replicate exactly the sound waves. And if you do this, and if you, for example, think of the speakers as a point source, you only have to adjust the time delay and level at in the right way to generate such a curved wave form. And this then creates at any point behind of this line, of this speaker line, exactly the same impression as if there would be one source, one point source. So if you look at the formula, what happens to generate the driving signals of the speakers along this line, you have to following up this formula, but this is quite complicated. So if you split it up, it makes the whole story a little bit more simple. So this part here actually says, no, this one gives you an answer of the delay, how to set the delay for these different speakers, depending on the room where they are located at. This part, actually this part, is dealing with the scaling, with the amplitude. So what amplitude has the speakers to follow up to generate this virtual source, this point source. And then there is also a 3dB filter. And that's about it. So, but if you look at the, first of all, complicated formula, then you just have to filter any input signal with the 3dB filter, scale it, and delay it. And if you do it in the right way, you got the perfect impression of having a point source anywhere in your source room, wherever you are. So, it looks quite complicated, but if you dig into it, it's actually not. So now, if you have a signal flow, you can use this 3D EQ filter for the input signal, then you split it up, and for each speaker, you have now one amplitude and one time delay. And that's about it. This is the whole story behind wavefield synthesis. This is now also the block, the unknown block that we said with the question mark to make the room compensation. So what are the properties of the wavefield synthesis-based system? So it's able to generate arbitrary wavefields, but there are limitations. For example, it has to be a circular speaker array or several line arrays to be used. So not an arbitrary speaker setup is allowed. It is well understood, and the mathematical foundation is well understood by now. It is especially useful for mid-size or large venues, but not so much for small areas. This means this is not probably good fitting for a home audio system, because there we have a sweet spot which is known, which is also a small area. So wavefield synthesis is usually better suited for big venues like cinemas. And there they are also used in several locations, as well as theaters and so on. They can be used as data and model driven realizations, and therefore enable acoustic rendering. So they have an excellent reproduction of points of source localization. So now let's come to the last part, and this is the higher audio ambisonics. The basic of higher audio ambisonics, I mean, wavefield synthesis was based on plane wave decomposition, whereas higher audio ambisonics is based on spherical harmonics. So I just showed you the spherical harmonics here in this picture up to the fourth order, meaning those are, let's say, the basic waveforms behind. Though this meaning you can combine those wavefields, those basic spherical harmonics, and build any arbitrary wavefield out of it. It's very similar to Fourier transformation. So there you have also basic functions. It's sine and cosine wave. Then you can make any complex signal at any frequency. Here it's almost the same. So instead of sine cosine waves, I have the spherical harmonics. But if I scale them in the right order, I can make any wavefield that I like. So the math behind is first of all, I want to talk about the spherical harmonics. How are they mathematically described? So they are actually, you can split it in two parts. The first part deals with the horizontal occurrence of the spherical harmonics, which is handled by the so-called ligand functions, and also in the vertical part, which is handled by the trigonometry parts, the sine and cosine wave, to make the real and complex part out of the spherical harmonics. So therefore, this is controlled by the sigma parameter. Sigma parameter 1 means we are dealing with the real part of the spherical harmonic, whereas sigma of -1 is saying that we are dealing with the imaginary part. So therefore, we have the three components: the Legendre function for the horizontal, for the azimuth description, the trigonometrical functions for the elevation, and the sigma parameter to describe the real and complex part. But this is not the whole story. The higher audio ambisonics is based on the Fourier-Bessel series. And there, the spherical harmonics are playing just one part of it. The biggest part of it, this means the whole coding is done in the ambisonic coefficients or ambisonic signal. This is here described by B, the matrix B. What is it doing? Actually, it's just a scaling. Actually, as you can look here, it's frequency independent, ideally. Meaning that you only have to scale the spherical harmonics in the right way to generate the desired sound pressure at a desired location for a desired frequency. Depending on what wave form you're interested in, the other parts here, this means the radial function. This means to describe the distance from the focus point. I don't know, how is the wave field behaving from the center point 1 meter away. This is handled by the radial function. And the radial function depends whether you are dealing with plane waves or that, or if you are dealing with spherical waves. So if there's plane waves, you have here's a spherical Bessel function of first order in first kind. And this describes the wave field in a certain distance. If you, but this is only good for the far field. If you're in the near field, you have to use, instead of the spherical Bessel function, the Hankel and Neumann function. So this means the spherical Bessel function of second and third kind. And this is then able, and then you're able also to describe wave fields inside the circle or outside the circle. Okay, how do such radial functions look like? So what you can see are the Bessel function of first kind for different orders. And if you really look, if you closely look at the peak, where does the peak of those orders appear? You can recognize that they appear either at further distances, if you take if you leave the frequency at the same number, or at higher frequency if you just look at the same radius. So both is handled here. Meaning that the higher order you're using to generate a wave field, an arbitrary wave field, using higher audio ambisonics, the higher the frequency, the whole stuff really works, or the larger the radius is, the whole stuff works. So this is actually the meaning behind it. So now I give you an impression of how this or how can this be looked like. So now I keep it only simple. I go into just one plane, not 3D, just into the 2D domain, and I'm just taking the zeros and the first order higher ambisonic functions. And now I would like to mimic a radiation from one direction. This is the source direction, indicated by the arrow. And if I go from the center to this desired source direction, then I have these crossing points. And those crossing points are exactly giving me the the gains necessary to scale the basic spherical harmonics in order to generate a final wave field mimicking a source being exactly coming exactly from this position. Okay, but why do I need higher orders? As I said before, first of all, I can increase the spectral range, or I can increase the sweet spot area where it works. But also another thing is important, and this means localization accuracy. And this is seen following now two different sources, using on the one hand only higher orders up to once, or higher order ambisonics up to once, and up to and the second order. And what you can see is, if you have two sources placed beneath, the difference of the gains are really minor if you only have first order. This means you have a higher blur. Whereas if you have higher orders, then the difference between those two sources are much higher. So you can distinguish between sources that are close by much better if you increase the order of the spherical harmonics. Okay. If you now want to decode, we overlay, or we use a circle of speakers. We do exactly the same what we did before. So this means we go from the center line to each speaker, and we have the crossing sections which reflect the amplitudes which account to the speaker. Following this approach, okay, what I also have to mention is, you see here, for example, from the Y component, a red and a blue one. The red one is indicating the imaginary part, whereas the blue part, the blue one is imaging the real part. So if you now count the crossings and took this gain and distinguish between real and imaginary part, you have exactly the gains necessary that one virtual source comes exactly from the direction where the speakers are placed. Okay, following up this procedure means that I have a source signal which is which has to run over the inverted re-encoding matrix, then weighted by the ambisonic signals, and then I have also another possibility to create, let's say, a taste factor of it. So this is the diagonal matrix defining the decoder variant. So there are different variants of decoder. For example, the in-phase decoder, the basic decoder, or the max RE decoder. The max, also the basic decoder, for example, is maximizing the sound energy vector. Oh, here's an error, because this is max RV. So because this is maximizing the velocity, the sound pressure velocity vector. The velocity, I mean, now I have to really go back a little bit into basics of psychoacoustics. If you know that our hearing system, at least at lower spectral areas, is using time differences for localization, whereas at higher spectral areas, it's using the level differences. So the velocity actually accounts to the time differences, whereas the energy vector is accounting for the level differences. And depending on the spectral area where you are, it is sometimes better to have the velocity vector maximized instead of the error vector maximized. And so therefore, you should use a mixture of both depending on the spectral end where you are. But on the other hand, if you are using, or if you have the aim to extend the area where the whole decoding should be perceivable, you should use the in-phase decoder, because here I have a much higher blur of the localization accuracy, but the area where it is valid is much bigger. So it depends what you want to choose now this decoder variant. And then by now having the possibility to manipulate the wave field, we can add effects as we like. So we can rotate, we can extend, we can do more or less what we want with it, having it in this form. So therefore, here the rendering happens. So we can move a virtual source then wherever we would like to do. Okay. So with the higher order ambisonic systems, we are able to generate, like with the MIMO as well as with the wavefield synthesis, an arbitrary wave field. But here the limitation is that we have to use a circular speaker arrangement. It is also nowadays well understood, mathematically at least, and it is useful especially if the area where we would like to reproduce the desired wave field is small. This is quite good for example, a living room where you know where you sit, or especially for a car where you know where the people are placed at because you are buckled up. It is basically it needs regularly spaced circular or spherical speaker, depending whether you want to decode it in 3D or in 2D or 3D. Depends. So it's very flexible. You can do both. And what's also very interesting, just recently there had been some investigations from the University of Graz in Austria, and they found an algorithm able to bring the higher audio ambisonic system, which is usually based on circular speaker setups, and can cope with arbitrary speaker setups. Therefore, this new finding is very, very helpful if we really have to deal with arbitrary speaker setups like in normal listening rooms. And it is also, like the wavefield synthesis method, data and model-based. No, both are possible. So data and model-based realizations. It has not found its way to commercial use nowadays. So it's mainly academic, academically solutions. So many universities they do investigations using higher audio ambisonics. Mainly based in Great Britain as well as in Austria. There are some big clusters, but I think the theory behind and the new possibilities, especially with this new Allrad algorithm, is really stunning. And it is the only possibility. I mean, also the wavefield synthesis cannot do it, but following the ambisonics theory, it is the only one that is able to encode arbitrary wave fields. So following this method enables one to really measure at any place, anywhere, the wave field and can encode it such that you can decode it in any place you like. No other possibility is enabling this. So now coming to the outlook. So if we analyze the audio chain, it could be shown that the room exhibits the part with the highest chance for further improvements. Or to be honest, it's the interaction between speaker and room. Thereby the challenge is to bring the real target room in line with the room as expected by certain standards. The current method of room equalization points to the current direction, but cannot deliver sustainable, satisfactory results. Auralization, respectively acoustic holography method, could be found to realize the desired room compensation in a mathematically defined way. With the right measurement device, even today, a MIMO system is able to do this. And using higher audio ambisonics, where the measurement is also defined by the ambisonic theory, we can now also encode any wave field, and that can then be used using MIMO, wavefield synthesis, as well as high ambisonics. So it doesn't have to be only one of it. So because the wavefield, the high audio mesonics and the wavefield synthesis, they can be transformed in each other by using the plane wave decomposition. So other methods like the wavefield synthesis or high audio ambisonics offer a high grade of flexibility, but still find coping with arbitrary speaker setups difficult, as I said. But there are solutions on its way, for example, this Allrod method. So it can be expected in the next coming years that one of those solutions might find its way to really home audio. And one of those solutions I want to present also by the end of this talk could look like this. So this one could actually be one of the solutions that can also handle the problem today. As we heard, nowadays the MIMO system is the only one that can really handle arbitrary speaker setups, whereas the wavefield synthesis as well as higher order ambisonic systems are the only ones that are able to enable acoustic rendering. So now if we put both together, we can have a MIMO system mimicking all the higher order ambisonics components. Having now the components at one position, enabling us with the right ambisonics coefficients to place virtual speakers anywhere we like. Therefore, if you remember the other slide where I showed you how a 5.1 could be realized using the MIMO system, now multiply it by the desired number of higher ambisonics, and then you have a version that could be realized nowadays and could also it is also be able to make acoustic rendering possible nowadays as well. I mean, it's a whole lot of computations that has to be done, but it is possible. So with this, I come to my end, and thank you for your attention, and if you have any questions, please let me know.
So could you walk us through an example of how you would do that? For example, how would we make this room sound like the Sydney Opera House?
With the solution I offered, this would be not possible. But if you only take one spot, and it's okay, I want to sound this spot like the opera house, it is possible, yes.
How would you take the data, process it, and generate that?
I mean, there are, to me, there are actually two possible ways to do it. One is the one I showed, and the other one is this Allrod method. But I would definitely, first of all, concentrate on a single spot, on a sweet spot, and then maybe using this method, I can also explain it in more detail right now. So this means I go to the opera house, maybe the best spot that I can find there, makes a measurement with a spherical microphone array to get it encoded. Use those encoded sound material. Actually, it's not depending on the sound. It's only depending on the room. So this means I take those ambisonic coefficients that I found, which actually describes the acoustics there. I place speakers around the spot where I want to make it sound like this. I make with the same measurement device the measurements again from each speaker to this position. Again, I have the ambisonic coefficients. Then I can use both, make the coding, the coder out of it, and then I play it over the speaker, and that's it. I hope it was understandable.
I think there's probably a little detail behind that, but yes, that doesn't.
It's not as easy as it is said, but it is possible. And we did some of it in other areas, and it is, let's say, it's promising. Any other questions?
Depending on the application, sometimes we need to specify the change of, I mean, that's sometimes I'm looking at the wall, right?
Oh, is there a microphone? It was really hard to understand.
Try to louder. Okay, so I mean that they are dependent application. So sometimes the sweet spot can be changeable.
Yes.
Yeah.
Yes.
And do you have any idea how to define the
Yes. I mean, if you have the possibility of rendering, it would be possible to track. And if somebody is changing, you can also change the acoustics. So this is, but then you need rendering possibilities. If you don't have rendering possibilities, for example, by using just MIMO systems, it is not possible. But having rendering systems, for example, a tracking camera, then you can take this information and combine it with the codings that you have, and the final result would be a trackable virtual sources. All these 5.1 virtual sources would just move with you.
Could you say a word about the computational power that's required in order to process the information from a spherical microphone generated filters? Is this something we can do with today's desktop PC?
Yes.
Can it be built into
normal PC?
Built into some electronics or?
I can, first of all, I can say that a normal PC is okay, no problem. And I can also say, if you limit yourself to certain orders, for example, you could still do it with normal DSPs nowadays. So it's nothing that we have to wait for the future. It's already there, and it's computable. Yes?
I have two questions. First thing is like, usually the practice when I set up a new AVRs or speakers, I do the equalization. But if I don't change anything in the room, do I need to repeat or something?
No, unless you do not change things, not. But if you change anything, you have to repeat it.
In
Yes.
the room?
Yes.
So like furniture or whatever?
To be very exact, you should do it whenever you change anything. But in practical terms, I would say, if you change the carpet, who cares?
Yeah. And also, some rooms, have different ceilings, high ceilings or tilted ceilings. Does it matter when you do the equalization, or actually it's only to a certain height, depending on the microphone? For example, my colleague came to my house. He said, "No, this is not acoustically good for anything because I have a high ceiling."
Yeah, I mean, as I said, I mean, I cannot beat physics, but I can make the best out of the things that I got. That's it. I mean, if you had really bad speakers, for example, I cannot make good speakers out of them. If you have an acoustical surroundings that is acoustically not well treated, for example, this system can help, but it cannot make it sound beautiful.
But the sweet spot can be limited. Still be good, right?
Yes, and it will be. And this is one of the advantages of the higher audisonic system, because if you take, for example, the wavefield synthesis, it can only operate, I mean, of course, depending on the number of speakers, the distance of the speakers, and so on, but normally around 1 kilohertz or so. Whereas the higher audio ambisonics, they can reproduce the wave field in its complete spectral area at the center, but only on this little spot. And then it depends on the frequency, how big this area is. The lower the frequency, the bigger it is. The higher the frequency, the smaller the area becomes. But if you take the size of the head into account, 2-3 kilohertz is no problem.
Thank you.
You're welcome.
I probably have a small question. Did you think about incorporation of this advanced method with the concept of a smart home? I guess it would be a sort of a computational engine already available, and you probably can use it to...
It's a good question. Actually, I never thought about it. So I cannot give you a decent answer, to be honest. But I assume that it can be well connected together, especially if I just listen to one of the keynotes before, having cloud computing available, connecting this with this computational power where those solutions ask for, I guess there are good possibilities. Or if you have a smart home that can track or that knows where you are, this information can also be used to adjust the system to in its best way. So yes, I think there are interconnections, but I cannot give you a clear answer how to do it.
Okay, excellent. Are there any other questions? So we would like to thank our speaker very much for, I think, an excellent tutorial. Thank you.